So let me give you just a little bit about my background. First of all, my bachelor's degree is in trumpet performance. That is a fact. I did make a switch, however, obviously. I got a computer science Ph.D. I spent 5 years after my PhD at the IBM Almaden Research Center down the road. That was quite a while ago, I'm afraid to say. And I've been at Stanford so far for 22 years as a regular faculty, assistant professor, associate professor, full professor, and so on. Recently, I've been mired a little bit in administration. I was the department chair of computer science at Stanford for about 5 years, and I'm currently a senior associate dean of engineering. Now, so that's about a 30-year career, and I'm obviously not going to be able to cover the whole thing in an hour, but I will actually split this talk in two, and I'm going to talk first about research and second about teaching, roughly 50-50 time-wise. In terms of research, I'm going to talk a little bit about how I have found research topics, a methodology I have for the research I conduct, and I'm going to give you some examples throughout that part of the talk. On the teaching side, I'm going to talk specifically about the emergence of the MOOC movement, the massive open online course movement, which I was involved in back in 2011. Now, the talk is called Magic Moments, and every once in a while you will see the spinning MM, where I will show you what I consider to be a particular magic moment. Okay, so let's launch right into finding research topics. So I would say I am not a visionary. In fact, I'm going to emphasize that big time. I'm not a visionary. But as a faculty member in computer science, our primary purpose actually is to conduct research and generally to build groups and have research groups having impact on the field of computer science. So if you're not a visionary, what do you do if you're in my job? Well, what I think I did, so I have launched a series of projects I would say were pretty successful. And what I did is actually found a recipe that has worked for me in developing research projects. I've really followed that recipe several times. Now, I would say this recipe I'm going to tell you about works very well in my area of databases and information management. I will warn you that maybe it doesn't work as well in other fields, although I've given this talk a few times and many people have come and said that same recipe works in my research area or would work in my research area. Okay, so what's the recipe? So I am in the area of databases. I've been working in databases since I started at IBM Almaden. And my recipe for a research project in databases is to take some simple but fundamental assumption underlying the way database systems work. I'm going to give you some very concrete examples of that. Find one of those basic assumptions and drop it. And in the world of databases, and especially database management systems, the software, there are a number of assumptions where if you drop them, I sort of think of it like pulling a piece of yarn out of a sweater. Things just keep unraveling and unraveling, and you have to sort of rebuild the whole thing. So when you drop these fundamental assumptions, you really, in most cases, have to reconsider everything that people think about in databases, which is mostly about managing your data and processing queries over that data. So this has the advantage in the academic setting if you have to reconsider all these different aspects of having many PhD theses. So this student will work on that aspect that has to be reconsidered. This student will work on that one. And I also have very much enjoyed during my career having research projects where we build research prototypes. And that when you drop these assumptions, you often you can have the opportunity to build a whole new prototype from scratch. All right, so let me get a little less abstract here. I'm going to give you several examples of a simple but fundamental assumption that underlies database systems. And these, not coincidentally, are some of the assumptions that I have in my research dropped and created projects, research projects around. And these go more or less chronologically. So the first assumption that I'm going to talk about is the fact that database systems, the traditional relational database systems, are based on the fact that you declare the structure of your data in advance before you start loading the data or doing anything with it. Now, you can, add a column or take a column away. You can make some schema changes, but that's often a major headache. The premise is, I'm going to know what my data is going to be structured like before I'm going to do anything with it. Okay. So we dropped that assumption, and we started working on what's called semi-structured data. It was also called, at the time, schemaless data. So semi-structured or schemaless data is working with data that you really don't know what the structure will be like in advance. It might be highly irregular. The structure may change frequently. And that really changes everything about how you store the data, how you index the data, how you process it, and so on. So there's one example. Second example. People think about databases as being these large, these large sets of data that you typically put on disk or somewhere. The data sits there. It changes sometimes, but the data sits there, and you ask questions over the data. And that's the traditional assumption underlying the database systems. Here's a different model completely. The data is coming as rapid streams, like a fire hose of data shooting at you. And the queries are the things that actually sit there. And as the data streams in, the queries give answers. Kind of flips the whole thing on its side. Again, if you drop that assumption, there's a whole bunch of things to work on. So that's the area of data streams. Two more examples. One of them is that data elements contain known values. If you think of a traditional database, it's going to have in the cells a number, a name, a photograph, whatever. But the truth is, in a lot of databases, the information is not always so precise. So we worked in an area called uncertain data, where you might not know precisely what the values are. Maybe they take a range. Maybe they're one of two possible values. Maybe some data is present or absent. I'm going to dig into this area a little bit later on. And the last one I've been working on recently, says there's an assumption that data is processed and gathered by computers. And of course, that's the predominant mode. But sometimes data needs to be gathered by humans. Or sometimes humans need to do certain things with the data. Sometimes you might have two pieces of data, say two objects, where really a human is the only one who can tell you whether those two objects are the same. Or maybe a human is only the only way you can find out certain things about images. And so an interesting area is to look at database management, where you have to periodically get humans involved actually in the gathering and the store and the management of the data, or the processing of the queries. And we call that crowdsourced data. Okay, so those are 4 examples. In every one of those, I would say, again, think of that thread. You're taking one assumption, but everything falls apart when you pull on that thread. I said you need to reconsider all aspects of database management and query processing. Here are some example aspects, and I'm going to come back to these in a moment in a different setting. But the data model is how you structure your data, such as a relational data model, graph data model, document model. The query language is the language that you use to ask questions over the data, SQL, for example. How is the data stored? How are indexes created on the data? How do you process queries? One of the most important aspects of database systems is the query optimization. In fact, I've always said the 2 most important things a traditional database system provides is query optimization and transactions. And query optimization takes the fact that queries are generally in a declarative language. They're expressed at a very high level. They can be executed over the data in many different ways. And the query optimizer is the one that is the component that finds the most efficient plan for executing the query before it starts. And a good query optimizer can make many orders of magnitude improvement in performance. So that's really important. Concurrency control and recovery, as I said, transactions are very important. And then application and user interfaces. So this is sort of all the things that you have to reconsider when you drop these assumptions. Maybe not every single one for every dropped assumption, but for each one, most of them. And again, you can sort of see where a student's research can slot into those. Okay, so I would say, I'm going to flash up my first magic moment. My first magic moment, I would say, is finding this recipe and sort of realizing that this is a way of generating really challenging and interesting research in databases. Okay? So, any questions so far? Yes?
When you say from the very beginning, you said you're not a visionary.
Right.
Why do you say that?
Why do I say that? Because a visionary sort of ponders the 10, 20-year future and thinks what are things going to look like then. Where I guess I'm more of a let's look at what's happening now and let's look at what isn't working for people and let's think how to make that work. I think it's a little bit of a different mindset. Yeah. Yeah.
Regarding one of the threads you dropped for the semi-structured data.
Yep.
So what do you actually
think? I'm going to come back to that topic actually with some examples. So why don't we defer? Yeah, because I'm going to get very concrete about that particular one. Yeah.
The emphasis seems to be on the students rather than the faculty can take care of themselves.
Oh, so the mode of research at a place like Stanford is the faculty runs a research group of students, usually PhD students, some undergraduates, sometimes some postdocs. We're managers, is the truth, of research projects. Yeah. So that's just the typical way that we operate. Yeah. Yes?
Every time you dropped an assumption and did some research, on an average, how long did that research last?
5 years.
So is your recipe sort of saying that, you know, be prepared to spend 5 years for every assumption you're dropping?
Sure. I mean, I'm being a little black and white here, but that's the rough granularity. Yep, seems to be. Also happens to be about how long a PhD student takes to start to finish, coming back to those students. So. All right, let's talk about how to approach a new topic. So let's say we've got one of these topics now. What are we going to do? As I said, we've dropped an assumption. It's time to reconsider all these aspects of a database system. And I'm going to actually divide these a little bit. First, I'm going to say, when you start working on a new area in databases, it's really important to think first about the data model. And not everybody does this. But really, if you're going to change the kind of data that you're working with, you have to understand exactly what that kind of data is going to look like. And I'm going to give you examples to show that that's not always such an easy thing actually to figure out. Once you know what your data looks like, the next thing is to design a query language. That's the language by which you ask questions over the data. And then I'm going to put all those last things as just a matter of implementation. Of course, it's not just a matter, but these really all go together in implementation because the model and the language is what the system is about. And I'm going to actually go one more step now and divide this into foundations and implementation. This is figuring out the foundations of what you're doing, then you're actually implementing it. And I'm doing this to make a point, which is that I have a personal belief that it's quite important to really work on those foundations before you start coding. That's my belief. Not everybody does it that way, but that's my belief. And I'm going to go so far as to say I built my entire research career on taking this approach to those problems. Okay? So I'm going to say that's another magic moment for you. Okay, so now we've been pretty abstract. I'm going to start getting a little bit more concrete. Okay, and I'm going to talk specifically about this idea of foundations followed by implementation and forcing oneself to work on the foundations first. Because I would say in the world of databases, we had a very dubious beginning to the idea that you might know the foundations of what you're doing before you start coding, and then very specifically in the SQL query language. How many of you know SQL? Good, we're going to do some SQL. All right. There's some nasty stuff in SQL. Okay, so SQL was meant to be a declarative language, and I've already talked about that. What that means is that you have a language, you have an understanding of what the meaning of queries is, the semantics, that's independent of how you execute it. So you're not saying, open this file, go through these records, open this other file, match up the records. You're saying, I want to do a join and a selection. That's what the SQL language is meant to be. And that's what query optimization is all about, finding the best execution plan for a query. Okay. Not everybody thinks of the SQL language that way. In fact, I think for some, they really only think about how it's executed. And this can cause problems. And I'm going to give a couple examples of those problems. All right, now we're going to get very concrete. We have a table called T. T has one attribute. I think I might call it A. I can't remember. And we are going to write an update command to decrement all the values in T that are below average, okay? Easy. If I ask you to write that in SQL, I think most of you could probably do that. Oh yeah, it is called A. I update table T. I set A to be A minus 1, where A is less than the average value in T. Okay, everybody with me here? Even if you don't know SQL, you're probably with me. All right, we've got 3 values in our table T, 4, 1, and 2. And we run this update command. What are the values afterwards? all negative numbers.
Your average is going to go down every time you decrement one of those values.
Yes, so you've jumped ahead to my second example. That actually doesn't happen with this one. The average goes down, but since we're asking for less than the average, that doesn't quite get us into trouble. That gets us in trouble when we're asking for greater than the average. You've stolen my thunder. No, seriously, what is the answer? It's not all negative numbers. Any takers here? So I think we agree that the average, that 1 and 2 are both below average, right? Okay, so what is the answer?
401.
401. Everybody agree? Okay, if you wind back to 1980, not every system would give you 401. Why not? Because they were thinking about execution. So you thought about the meaning. You said, okay, I know the average is going to be something, greater than 2. So these are both going to be decremented, and so they'll be 0 and 1, right? All good. Now think about how the system might execute it. It says, okay, I'm going to start looking at 4. Is 4 below average? No, so I'll leave it alone. Then next I'll go to 1. Is 1 below average? Yes, I'll make it into a 0. Next I go to 2. Is 2 below average? Oops, it's not below average anymore because it did these one at a time. Okay, so I'm going to tell you that in the 1980s, if you get 2 systems and you ran this query, or this update, you might get one answer on one system and a different answer on the other. That I consider bad news. Okay, now, all right, so here's the other example, which was what you were thinking at. If we want to decrement the above average values in table T, it gets even worse. The second execution plan, the one that did it one tuple at a time, can actually go into an infinite loop, just constantly decrementing with this particular one, where I know we understand that's probably not what should happen. Okay, but all of this got fixed, and that's great, except that was 1980s. Now we are, what, the 2016s. We still have some queries where 2 different systems will get different answers for the same query. And it's even worse. The same system might get a different answer today and from tomorrow without anything changing in the database. Okay, seriously. All right, so I'll give you this example. So regional average temperatures. So we're going to have a table that has regions, and it has temperatures, and it's also going to have cities in it. And here, let me just put the data up right here. We're going to have the region of the West that has Seattle 50, San Jose 70, the East with these 3 values. And we're doing a standard group by aggregation. Okay? We're doing the standard, give me the region and the average temperature. And so I think you can see all clearly, this is not the problem yet, that it would be West 60 and East 15. That would be the answer. All good. Now, what if we add city here? What if we add city? Now, what do you think should happen if we add city to this query? Anybody, what do you think should happen?
The same row should be repeated for every city.
That would be one possibility.
5 rows with 2 averages.
Pardon?
All the 5 rows, the city by C.
Yeah, that's what he was also suggesting. Any other? I have a very strong opinion about
It
this.
should be in the group by clause.
Should produce an error. You're doing a group, and then you're asking for a city out of the group. What city do you want? So this should produce an error, and in some systems this produces an error. But in other systems, it picks a random city. In fact, I think it usually picks the first city it finds as it's executing the query. Furthermore, if the data structure, if the file got reorganized, this is the example, between today and tomorrow, which should never affect the result of a query, you might actually get a different answer without the database ever changing. Okay, so I consider this really bad news. So this is to show that I think in databases, and it's not the only field, there has been, not everybody always follows the idea of really thinking hard about foundations before doing implementation. Now, some of it may just be product pressure. I do have the luxury of being in academia where I can think about foundations pretty much as long as I want before we launch into implementation. Okay. And I was going to go into some examples from some of the work I've done that are roughly in this area. Any questions at this juncture? Okay. So when I started working at IBM Almaden, I started working in what was called the Starburst project at the time, which is a follow-on to R-Star, which is a follow-on to System R. And my niche was to start looking at what we called at the time active rules, which became known as triggers. So triggers in a database, probably most of you are familiar with them. You say when some action occurs, activate the trigger, check if a condition holds, and if it does, perform additional actions. And in SQL databases, typically the actions that are being monitored are insert, delete, and update. The conditions might be expressed using SQL, and the actions expressed using SQL. I'm going to be a little more abstract in my example. Okay, so here's a warm-up example. We have a database that is tracking people selling stuff. And we're going to have one trigger that says, when new sales are inserted, if they're greater than 50, give the seller a bonus of 100. Okay? And then we're going to have a second trigger that says, when new sales are inserted, if the total exceeds 1,000, then everybody gets a 10% raise. All right? Those are the two triggers. Okay. Here's our example. We have 3 sales that are inserted: Mary 600, John 300, Mary 400. Okay, what happens?
Is it a single transaction that they're done on, or?
Well, this is part of the issue. You're going to keep getting ahead of me here. This is okay. You could think of these as a single transaction. Sure, 3 inserts, but but don't get into the deferred triggers and all that. Just I know. That's
Stonebreaker works.
Well, I'm going to talk about Mike Stonebreaker in 2 slides. Okay, so all right. Okay, anybody want to venture? This one is not hard. Okay, this one, Mary gets 100 bonus because she had a sale greater than 600, and then both get a 10% raise because after the last sale, it went over 1,000. And I think we're all in agreement that that's what would happen with this. This is the easy example. Now let's look at a tricky example. I've made one change up here, which is the seller gets a raise, not a bonus. Okay? And then I've also changed these sales so that there was 800, 300, 600. Okay. All right? So this actually brings up a whole bunch of things, like how many raises does Mary get? Does she get a raise every time she sells more than 500 only, or because she sold more than 500 in this batch? How many times is everyone's salary increased? It goes over 1,000 here, but then it's still over 1,000 there. So does every time there's an increase? And which of Mary's salaries is the 10% applied to? Okay? So these are all questions that need to be understood, and this is a lot more complex than just understanding SQL queries. So if people were bombing understanding SQL queries alone, imagine trying to deal with this. And now I'm going to talk about different approaches to this problem. So I'm going to go way back in my history, and there I am at the IBM Almaden Research Center. If you recognize it, fresh out of graduate school. That's how I looked, maybe somewhat younger than now in any case. And I actually, in graduate school, I worked on programming languages, so I actually did have this sort of predisposition to think about these foundations. So I was working on these triggers. I saw immediately that it was very complicated, so I would sit here and think about things that I was calling transition tables and conflicts between triggers and whether different orders would have confluence and end in the same state. So that was what I thought about while I was there. Then there's this guy named Bruce Lindsay. Anybody know Bruce Lindsay?
Yeah.
Okay. So Bruce, I see a scary-looking guy. He would stand outside the door that I went in and out of smoking, so that's why he was standing outside. And every time he saw me, he would wonder how my coding was coming along. So he would be there sort of growling at me to write code while I was still thinking about these foundations. Then across the bay at Berkeley was Michael Stonebreaker. And Michael Stonebreaker had a competing project at the time. So we were working on Starburst, he was working on Postgres, and he was putting triggers into Postgres. And he announces, while I'm there thinking about all these things, that they had finished their trigger system ages ago. Okay, so I said to him, okay, what does it do? Or actually, more specifically, I said to him, here is an example of 3 triggers in a starting state. What would what's going to happen in your system when you do that? And his answer was, I need to run it to find out what it'll do. Okay. So that, I would say, was another magic moment. Now, obviously, he's a great researcher, and he's done great things. But I would say he kind of takes the opposite approach, which is implement first, see what problems you have, and then solve them. Okay, that's a different approach. Okay, let me do my next tricky area. Well, yes. Are you going to ruin my data streams one too?
I'm sorry. I work with Microsoft.
Oh, okay.
But there's the scruffy versus the practical, the unpractical people. But in any case, Ron Fagin gave a talk at Stanford today, and he talked about theory versus practical, and which side is this coming towards?
Yeah, so that's a great question. Is this theory or is this practice? I am definitely considered a practice person. I am not a theorist. But I do work on foundations before building systems.
So SQL doesn't seem to have a good theory behind it.
Well, there's relational algebra, which is a great theory, but the SQL has more than just relational algebra. People try to extend that theory, but yeah. But I would be labeled a systems person because we build prototype systems, even if we think about them a long time before we start coding. Yep. OK, and Ron is a theorist. Yeah. Though he has some very practical algorithms. Yes?
Before leaving, going to data stream, at the time of the SQL, there was Codasol, there were network databases. Can you give a little color on?
Roughly before I was born. Yeah, go ahead.
Yeah, around that time. You know, so, but why do you actually think that like SQL, SQL, besides government contract, made the leap?
Oh, I actually think because it has really good foundations, because it's based on a set theory and it's based on an algebra. So, and it's very simple.
To play the other side, Codasol, network database, financial system continue to use it even today.
Yeah, my personal opinion is that the reason relational databases have been so successful is their simplicity and the big separation, even if it's flawed at times, between the storage structures and all that and the way you express things and understand things. Yeah. OK, data streams. I'm going to be fairly quick with this one. So here is an example data stream. We have a temperature sensor that's giving us some measurements along with timestamps. 4 o'clock, 72, 4:15, 74, 4:20, 76, and so on. So it's a stream of time-stamped values from a sensor. And as I said, in data streams, you have a query sit there, and the query will give answers as the data streams in. So we're going to have a query that's going to give us the average of the most recent 3 readings. So at all times, I want a result of my query to be the latest average of 3 readings. OK? So I think we probably agree what would happen with this stream. When we get our first 3 readings, we'll have 74. When we get the next reading, then we'll shift that window over, and our average is 70. We shift over, and we shift over again. And I think everybody would agree that that's a sensible result for that query. OK? But now things get a little weirder in this scenario. In this scenario, for whatever reason, our temperature sensor gives us 3 values that all are at 4 o'clock. First is 72, 74, and 76, whatever reason. Then it doesn't give us anything. And then it gives us 3 values at 7 o'clock. We're going to ask the same query, the average of the most recent 3 readings. Well, again, there's been different people have been working on data stream projects, and there have been different interpretations of what this means without being super explicit. So in one system, it's the same answer. And actually, the system we built, that there is a linear ordering of these, so you have exactly those same things streamed out. But an alternative interpretation that's also reasonable is that when you have ties and timestamps, you assume that you don't know the order between them. And if that's the case, then the only reasonable answer for this query would say, first I consider the first 3, and then I don't do anything until I get those next 3.
You have only 2, like you said, pre-measurement.
Sorry?
It should be a third measurement.
There should be a third. It would go back before the screen.
Oh, that would go before, yeah, before the screen, yeah. So I would say this is an example that's really true to the present day, another example where the same query could be interpreted in 2 different ways, just like the original one we saw with SQL, and so it needs to be thought about. Partly what I'm just focusing on is the fact that this can be pretty tricky, these data model and query language issues. And here's my last one, and this one's going to get pretty technical, so fasten your seatbelt. This is uncertain data, okay? And if it gets too technical, I'm almost done with the research part. Okay, so this one's going to be based on an example where we want to solve a crime using our database. And our database is going to have 2 tables in it, or 2 relations. One is going to record facts that a witness saw a car at the scene of a crime, okay? So there might be a bunch of witnesses who saw a bunch of cars. And the other is a database about cars that are driven by people. Okay? And so when we want to generate suspects for the crime, we do, this is relational algebra, but don't worry about it, we do a simple join of those two. We're going to say a suspect in a crime is someone who drives a car that was seen by a witness at the crime. Okay? I'm trying to make the simplest possible example here to show my point. But we're going to add a little wrinkle, which is these relations might be uncertain. It might be that the witness thinks they might have seen the car, they're not sure. Maybe this car, we don't quite know who it's driven by because these are criminals and they might steal cars and so on. So those are going to be uncertain tables. Okay? So let me just say a little bit about uncertain databases before I get into my example. Everybody sort of agrees that the foundation of uncertain databases is that an uncertain database represents a set of possible certain databases. Sometimes that's called possible instances. So Kathy saw either a Honda or a Mazda. It says, okay, either Kathy saw the Honda or Kathy saw the Mazda. All right? Amy might have seen an Acura or maybe she didn't. So that tuple might be present or absent. A Honda might be driven by Billy or Frank, for example. And we're going to represent this concretely with alternative values for tuples and these question marks which say a tuple can be present or absent. All right? In the project where we worked on this, we also had confidence values or probabilities associated with these things. I'm not going to do that today. Today it's just going to be uncertain alternatives and presence or absence. So here's a concrete, here's the same thing. Here's a concrete representation of these two tables. The first table says Kathy saw either a Honda or a Mazda. The second says Amy might have seen an Acura. The question mark says this is present or absent. So there's 4 possible instances for this table, the 2 possibilities for the first one and the 2 possibilities for the second. This says that there's a Honda that was driven by Billy or Frank. So there's 2 possibilities for this table. So in total, there are 8 possible regular databases in this uncertain database. Okay? All right. Now, the dilemma that I'm going to tell you about is the fact that this representation, I call it a model, it's a representation, is not closed. And what I mean by closure, what closure means in databases, and it's generally an important thing, is that when you run a query on a representation, on a database, you should be able to represent the answer in the database. So you should be able to run a query over tables, and the result should be a table. Run a query over graphs, the result is a graph. Okay, it's considered a good thing. We're going to see that this model is not closed. I'm going to expand the data here to include 2 more tuples here. We're going to have Jimmy, who drives a Toyota Mazda, and Honda that's driven by Hank. Okay? Anybody notice anything about my data? Very high level thing. Male criminals, female witnesses. Just like real life.
It's
Yeah.
like Jimmy is able to driving 2 cars.
Pardon?
Jimmy is driving 2 cars.
This says that Jimmy drove a car, but we don't know. It's either a Mazda or it's a Toyota. So these are either or. Yeah, you can't have both of these at once. You have one or the other. Yeah, I make that very clear. This says that one or the other is true. This says it's either present or absent. This is the only tuple that's absolutely normal. This says definitely there's a Honda driven by Hank. Okay? All right. All right, so now we want to generate our suspects, so we're going to join these 2 tables. All right? And when we join these 2 tables, this is what we get. We get that Billy or Frank might be a suspect, Jimmy might be a suspect, and Hank might be a suspect. And if you think about it, that's what you'll get when you do this join, except this does not correctly capture the instances in the result. And this is the hard problem where I'm going to wait until somebody tells me, why is that the wrong answer?
So it might have been an Acura.
It might, no, actually it can't have been an Acura because there's nobody here who drives an Acura.
But the witness saw one.
Yeah, but we're joining. We have to have a witness see it and someone drive it. Yeah. You're on the spot. Why is this the wrong answer? Yes.
Because assuming we have one Honda here, sort of the Billy and Frank disjunction is in contrast with the Hank one.
Exactly. Yep. Well, actually, that one is not in contrast. In concert. Did you say in concert, or did you say? Well, let's say in concert instead. Okay. I think you're getting at the right thing here. The problem is that this allows us to pick and choose whether these things are present and absent independently. So this has how many possible instances? 2 for this, 2 for this, 3 for that, 2 times 2 times 3. But not all of those possible instances are actually possible. If Billy or Frank is a suspect, that means that Kathy saw a Honda. If Kathy saw a Honda, then Hank is definitely a suspect too. So we can't have Hank present and Billy or Frank absent. Basically, there's connections between these, or correlations between them. I mean, another example, if Jimmy is a suspect, then Jimmy must have, if Jimmy is a suspect, then someone must have seen a Mazda or a Toyota. Since there's no Toyota, it means a Mazda was seen, which means a Honda wasn't seen, which means Hank can't be there. So we can't have Hank and Jimmy at the same time. Okay? So that's the dilemma. And I will tell you, we actually proved formally that you can't capture the answer in this model, period. Okay? So what happened? What happened is we added to our model a concept called lineage. And lineage basically says, where do things come from? And in this, I mean, lineage is a general term. But what it meant for us here is that we add to an answer basically pointers to where the data came from. So we say, OK, Billy, if Billy's in the answer, Billy came because those two were picked. And if Jimmy is in the answer, Jimmy is because those two were picked. And then the meaning of this table with lineage is that you can only pick possible instances that have consistent lineage. Okay? I mean, this is complicated, but that's the basic idea. Okay. And we've proven that data plus lineage captures the correct possible instances and actually can represent any query answer. Now, the context is that this work was done in a project that we called TRIO, and we called it TRIO because it was data plus uncertainty plus lineage. But the history is interesting. The combination of working on a system, and this doesn't quite fit my recipe, I'll have to say, but the combination of working on this system that had both lineage and uncertainty was motivated purely by applications. We looked at scientific databases that needed that. Entity resolution databases needed that. We just seemed to keep coming across database applications that needed both, never imagining that lineage would turn out to be the key to representing uncertainty. Never imagined that. In retrospect, I think why, what happened? Well, one possibility is implicitly there's a connection in the applications between uncertainty and lineage. That's certainly possible, but it's not explicit. Maybe there was an unconscious hunch, when we decided to do this project with both of those. Maybe it was divine intervention or pure luck. Who knows? But I would say definitely a magic moment when that whole thing pulled together like that, to put those two sort of what we thought were separate pieces and have them be key to each other. OK, so to summarize the research part of the talk, I've given my recipe for a database research project, which is pick an assumption, drop it. I have a way I like to approach topics, which is to really focus on the foundations before going to the implementation. And I'd say don't skimp on foundations, because I think that in the world of data management, data models and query languages are a lot trickier than people actually think. OK, so that's the end of that part of the talk. Good time for a question or two before we move into teaching, which is going to be a complete switch of gears. Yeah?
So the last example that you showed, will graph database solve this problem efficiently?
Would a graph database solve it efficiently? It would not be the most efficient way to solve this. So yes, there were those pointers, but we didn't even store them as pointers. I mean, that was sort of logical. So a graph database would be good when you had no structure at all, but that was actually fairly structured. Yeah. Yeah.
One reminds me of truth maintenance systems.
Yeah, maybe so, although that would...
a vector of the assumptions that went into each conclusion.
Yeah, I guess that is what we're doing. That's true. Yeah, right. And now probably if you I mean, sometimes we would get layers and layers of lineage. We have to query over query over query. And probably the explanation for that last thing would be like a truth maintenance system. I think that's probably right. Yep.
How does this compare to, I think, maybe Minker? Just maybe my memory is wrong. Minker may have logic databases.
Well, I mean, logic databases are vaguely related, but not identical at all. Right. I mean, those are sort of Prolog-like things. Yeah. All right. Yes, last question, then I do want to go to the teaching part.
Structured query language is based on relational algebra.
Right.
So my question is, for NoSQL databases, do we need a separate language to deal with unstructured data, like big data, for example?
Well, I mean, there's no single data model for NoSQL systems yet. And some of them are extremely simple model, like just key value pairs. But yeah, as things get more expressive, I think it's very good to have a model in a language. Graph databases being a good example, where there's a variety of languages, some of which are very well founded.
So is there any work going on in that area?
Well, again, NoSQL, there's not one single sort of thing to work on yet. There's been a lot more focus on systems aspects there. Yeah. Yep. All right, complete switch, excuse me, of gears, which is to teaching. And I'll try to keep this a little shorter. We're going to wind back 5 years to the fall of 2011. And at that time, 3 Stanford computer science courses were offered free to the world. They weren't known as MOOCs, but now they are known as MOOCs. How many people remember the fall of 2011? Did anybody take one of those? AI, machine learning, databases? Okay. That was a very exciting time. And I almost didn't put my course on there as the 3rd course, but Andrew Ng convinced me to, and I'm very glad that he did. Okay, it instantly launched this online education frenzy, which I would say is still going strong. And now I'm going to tell you the one question you are not allowed to answer, which is where is it going? I don't know. I have no answer for that. And it's anyone's guess. So that question is off limits. I'm happy to talk afterwards privately, about little things, but just don't ask that question, because I seriously don't know where it's going. Okay, so back to 2011, it was the fall quarter. I was teaching my usual database class called CS 145. There were 150 students at the time. Now there's about 300 every fall. But I was convinced, as I said, to simultaneously put my course online. We called it DB class. I had actually already been working on preparing some materials I was going to do a flipped classroom even before this MOOC idea came around. So I was somewhat prepared in a variety of ways. But anyway, put it on there with those other 2 classes. 60,000 students enrolled. I think that number is meaningless. I don't like when MOOC providers, especially for-profit ones, start talking about these numbers, because that's how many people got an account. All right, who really cares how many people? My mother got an account. Okay. Here's more interesting numbers. 26,000 people submitted at least one assignment for grading. 6,500 completed the entire course. That's 10% is considered pretty good. I think 5% is more common these days. But I think all 3 of those courses were roughly 10% at that time. Since then, I've done 2 more instances of a synchronous offering of the class, and now I'll tell you later what I've done with the class. But overall, it's still sitting there. People are still using it actively. Rough estimate, about 500,000 accounts, but again, I don't think that means anything. About 8 million video views. About 600,000 assignments have been graded by the system, and 25,000 of these statements of accomplishment have been issued. Okay, anybody have a statement of accomplishment from the database class? 2 people. Okay, cool. All right. Let me clarify what online education means, because people get very confused with the terminology. So I'm going to start by doing that. There is this notion in academia now called the flipped classroom, sometimes called the blended classroom. The idea there is that the students watch the core material, they learn the core material on video on their own time, and when they come to class, they work on interactive exercises with the instructor. So it's flipped because you're doing the lecture on your own and the homework in class, okay? So that's that terminology. There's a concept of taking course materials and putting them online, but not having a synchronous offering of a course, and that's become known as self-study. And then there's a synchronous public course offering, which is known as a MOOC, or Massive Open Online Course. But key to this is that all of these actually rely on the same basic set of materials. Everybody's courses, if they do a flipped classroom, they do a self-study or a MOOC, they make videos with the core material, very often with embedded short quizzes in them to keep people's attention. There are quizzes that are standalone quizzes besides the ones in the video, maybe more complex. Many have automatically checked exercises of some type, and then there's support materials, slides, notes, and readings, and so on. Okay, so that would be used for all 3 of these. In my flipped classroom, when I taught it that way at Stanford, I used all those materials I just described. During the classroom time, I would do problem solving with the students, usually more advanced stuff. We'd have guest lectures. We'd talk about research or exotic topics that we couldn't do if all the lecture time was used for playing lectures, and have help sessions in the class. I also augmented the automatic online stuff with written challenge problems that the TAs would grade. We had a programming project, and we had real exams. So this is what the students got for paying Stanford tuition over the people who did it for free online. Okay. For the MOOC version of the class, same core materials. The exams were just multiple choice exams, obviously, so they could be graded automatically. There was a discussion forum, and then the statement of accomplishment at the end. And the discussion forum led to a lot of community among the students who were taking the class. And that's a big deal in MOOCs, is the community, I think. Now, I'm going to say that the first time I did the MOOC was one of the most invigorating teaching experiences of my career. I really got into it. It was really rewarding to have all those students taking the class, really excited about the class. People sent me flowers and chocolates and told me how they got a job and so on. In fact, I'm going to go as far as to say it was the most invigorating experience of my career, period, teaching that MOOC. So we're going to definitely give that one a magic moment. All right, just very quickly, what did this entail? Some of you have seen it, and it sounds like lots of you have seen other MOOCs. This is an example. I did a very low-tech MOOC, extremely low-tech. I sat in a room with a webcam and a little tablet. So this was an example from the video of a lecture. I did a lot of demos during the MOOC of database things in action. This is an example of a quiz that would pop up during this is about multi-value dependencies during the video to keep people's attention. You could skip it or do it. There's an explanation for the answer. One thing I want to talk about a little bit is the quizzing system that I use. These are for the quizzes outside of the in-video quizzes. Actually, for 10 years prior to my doing the MOOC, I used a system that was developed by Jeff Ullman at Stanford, which was called Gradients. And his idea was to have that, at least in the areas where we were teaching, you could create questions where you had what we called a root question that would have a lot of right or wrong answers. A lot of right answers, I should say. And so what I did for my class over that period is I had developed a database of quiz questions, and for each one, a set of right answers and a set of wrong answers. And each time a quiz was launched, it would choose one right answer and a bunch of wrong answers. And if you design this well, students get the impression that each time they press the button, they're getting a brand new quiz. They actually love it. It's really great for studying. So Jeff had that system long ago, and the pre-Coursera people, this was before Coursera existed, was some students building a platform, rebuilt that so that I had that. So for the MOOC students and for the classroom students, they could do these quizzes over and over. It would look like they got a different quiz every time. They did get a different quiz every time, and that was highly appreciated. And we let them just do it until they get 100%. And then they can keep doing it afterwards to enforce that. And for program, we also developed automatic, not too sophisticated, but automatic checking of SQL queries. So we'd give them a query that they needed to write, and we'd check whether they got the right answer. We also did it for triggers and views. We also did XML queries. We did XPath and XSLT. So it was we built a lot of stuff. In that first MOOC, I also had a personal touch. So I got very involved in it. Every week, I would do what was called a screen side chat. Not everybody knows what it's referring to, but I think it was Franklin D. Roosevelt who did fireside chats on the radio and every week. So every week I'd get here and go on a screen side chat. There's actually a picture of a fire there for the very few people who figured out that connection. I would just go on there and talk about what we were working on and cheerlead a little bit, talk about what things could be skipped without losing the flow, what things might be particularly hard. At Thanksgiving, we had a turkey, and then here's the so-called winter time. The students were extremely appreciative of the class. Obviously you can't read these. This is the background of some of the students. This is a high school dropout. This is someone who's 71, 13-year-old freshman, and so on. This is all the people saying how much they love the class. If someone said I was a rock star, that's certainly the only time that's ever been said. And then somebody wrote a poem. An ode to Stanford. The students, they came rushing in from far and near and everywhere to gaze upon this wondrous thing, a precious gift for all to share, and it goes on and on. Okay, so that was very rewarding. And there was a top student in the class, a very clearly top student out of these many thousands. So this student posted 900 answers on the discussion forum. Every answer, there was no discrimination, was a hard question, a dumb question, whatever, no discrimination. Every answer was correct. Was of perfect length, it was perfect English, it was amazing. Everybody loved this student. That was a magic moment, having this student in the class. Here is the students in the class talking about Amy, that was her name. They're expressing their gratitude toward her. Somebody says that they think I'm her in disguise. This person made a marriage proposal to Amy in XML, actually. So it says, down on knees, the opening tag. So, so that was pretty amazing. And I'll actually say after the class was over, I looked up the student. I found she was a UCSD graduate working for her father's company in San Diego. I flew her to Stanford for lunch. I offered her admission to our master's program with a teaching assistantship, and she turned me down, which was, yes, disappointing. But it was still a great thing. OK, any downsides? I'm going to give you 3 downsides to the whole thing. First one was complainers. So there were the course ends, everybody gets their statement of accomplishment, and they're shocked that it's a PDF file, just a random PDF file. They say, what? I'm not getting some embossed thing. And worst of all, one person says, it doesn't say Stanford on it. And someone else said, yes, it does. It says, you are not a Stanford student. This was not a Stanford course. You did not get Stanford credit. It says Stanford all over it. OK. No, but there were seriously complainers. Then there were the cheaters. How do we know they were cheaters? We had multiple choice exams. We had 3 days for them they could do the exam. When they did it, they had a couple hours to do it. Some people finished the exam in 1 minute with a 100% correct score. How did they do that? They had multiple accounts. On one account, they took the exam, they wrote all the questions down or whatever, recorded it, spent a day working on it or whatever to make sure they could do it, and then they used their other account to get 100% instantly. Probably other forms of cheating, but that was the most obvious. And then the second and third time I did the MOOC, it wasn't quite as exciting. Partly it wasn't as new, but also now there are hundreds, thousands of MOOCs, and people take advantage. People sort of feel like they deserve them. It's not as, they're not thinking about it as a gift, I think, the way they used to. OK, current status, I took my full database course. It was a 10-week course. I divided into 14 mini courses based on topics. I've specified some pathways through those mini courses based on what topics you want to learn, on semi-structured data. Maybe you want to focus on OLAP. And then there's basic versus extended versus comprehensive. It's all self-study now, so no synchronous offerings. That means that it's always available, which is great, but there's no significant community among the people because they're all doing these different things at different times. But I do still get a steady stream of thank yous, which is very rewarding for me. And with that, I will say thank you. Questions about any parts of the talk at this point? Yeah.
What is the Stanford iLab?
What is the Stanford iLab? Is that the data science courses, or what? Oh, that! Oh, I was going to say, what is the Stanford iLab? That is actually, oh, you're not reading it correctly. That is the Stanford Info Lab. This is why, right? Yes, OK. I was going to say, there probably is something called the iLab, but I don't know what it is. This has been our logo forever. The Info Lab is a group of 5 or so faculty who do work in databases and information management. We call ourselves a lab. At Stanford, a lab means that you made a web page or a T-shirt. It doesn't mean anything official. Even the Stanford AI Lab is nothing official, and that's the lab of faculty who do work in databases and information management. That's all. Yeah. Other questions? Yes?
Going back to the structured query language, it's always logical, and you find out multiple instances where you can have different viewpoints. Has there been a research where you try to include an imperative part inside the logic programming just for the developers to clarify what he's intending to with that query? Like some sort of, like certain algorithms where you said the average keeps moving, it's based on the implementation of the algorithm.
Right.
Like, has there been a leeway or just a kind of a function that the developer can inject so that he can clarify how he wants the engine to perform instead of the query optimization just...
I mean, the only thing I'm coming up with here is query plan visualization tools, which you take a query, you send it to the optimizer. Most systems will, or bigger systems or whatever, will allow you to look at a depiction of what's going to be executed. Is that at all what you're thinking about?
No, I'm just thinking, why was the algorithm always abstracted? Why was there no...
I mean, why do you use a declarative query language?
Yeah, why?
Right.
Why has it always been like that?
Well, I don't think very many people think it's a bad thing to have a declarative query language. It's much easier to write the queries, but the key thing is that in the ideal world, this is not ideal, but in the ideal world, you have the storage structure of the data and the indexes on the data, and the person who's writing the queries doesn't have to know anything about that. But then you have to go, then they can't write the algorithm to actually do the query execution because they don't know what's there. They don't know how it's stored. They don't know what indexes to use. And so they're just writing this high-level query, and there's this whole machinery inside that takes that query and looks and says, okay, I have these indexes, and I have statistics that tell me how big things are, and I can estimate if I do it in this order, it'll take me 30 seconds. If I do it in this order, it'll take me a century, right? And that's all hidden. And that's really considered one of the grand benefits of a database system. So, does that answer the question? No. Okay?
I agree that's the advantage, but isn't there a hybrid approach that you ever tried out just to resolve these?
You mean to combine,
yeah, like just in situations where you find it out where there could be different viewpoints. Like just...
Oh, you mean like the query where there are two different possible... Well, but what I was showing there was just the fact that people weren't thinking about what they were doing. I wasn't arguing that you want the ability to have both of those. I think you should choose one and stick with it. Right. So I see what you're saying, maybe inject something in the middle where I can say I either want this semantics or that semantics. Ooh. Well, it's possible, but I don't think the issue is that there were these two different needs. I don't think in most of these cases it was that there was a case where you needed one semantics and another case where you wanted the other. I think it's just that people weren't thinking about what they were doing. Yeah.
It's harder to get declarative things right. And if you wanted to come back with sort of an answer to, I want a procedural way to do things, but I don't know the underlying tables, the model might come from the compiler optimization people. I see that I can switch the orders of this moving, therefore.
Right, yeah. So compiler people do know how to do that too. And compiler optimization is a little different than query optimization, but you're right. That would be some kind of intermediate language. And maybe that's the same thing you're asking is why don't database people have those intermediate languages? Well, I mean, there have been languages that are kind of intermediate, like Pig. Do people know Pig that's sat on top of Hadoop? It was kind of a half declarative, half procedural language. So there have been languages that combine declarative and procedural. Yeah. But you'll have like this declarative piece inside a loop or something like that. So I'm not sure they were motivated precisely by a desire to be at that place, but they have emerged. Yeah. Yeah.
What's next?
What's next? I mean, what am I working on now? Well, I alluded to, I've been working on this crowdsourced stuff where you're trying to combine human computation with data stuff. I mean, I could give you a very, very simple example. What if you had a bunch of images and you wanted to filter those images for something that only a human could do? How many humans do you ask for each image to get the quality that you want? There's generally a cost-quality latency trade-off, because you have to pay the humans, but if you pay more humans, you get better answers. And so we've been looking at a whole range of problems where you have that trade-off in figuring out, say I have a maximum amount of money I can spend on humans, how can I get my quality as high as possible? Another example, very easy to understand, is what if you want to sort things, but the human has to do the comparison operation? What's the most efficient way to sort? So that's the type of thing I've been working on lately. Yeah. Yep.
What led you to decide which assumptions to challenge?
Oh, that is such a good question. The good answer to that, and that's mostly true, is that you look at how people are being challenged using a system, and that's mostly what happened. You say, okay, I see these applications, they're really being constrained by the fact that you have to do the schema before you can load the data. What are we going to do? And at that time we were looking, that was in early days of the web, so we were starting to look at data extracted from the web. And we said, this is not working to try to put it in a database that requires the schema. So that was an example. Data streams, yeah, we could see people had streaming data sort of coming along, so that motivated that as well. So mostly application needs that weren't being met by databases, but sometimes just intellectual curiosity, I would say. Yeah. Other questions? Yeah?
Did you find from the course
Andrew Ng mentioned, analyzing the big data and finding perhaps flaws in how it was being taught.
Yeah, so I have not done that with my course, but there's a lot of work going on at Stanford now and many, many places, taking the data from the MOOCs. It's very fine-grained. You can see where people stop the video. You can see how many times they tried problems. There's a lot of detailed data. And the idea is that that could be used to, first of all, improve one's course materials, to understand where people had problems, but in the long run to provide customized, adaptive experience for people taking the courses. So that's a very important direction. I just haven't worked on that personally. I actually used some of the data we gathered there, though, for this problem that I described of combining humans and data, where we were looking at the problem of peer grading. So when you have to grade in the MOOC setting, if there's something that has to be hand graded, the only way to scale it is to have students grade each other. And so we actually looked in my research at algorithms for how many students do you have to ask to do the grading. We sort of imagine the students cost money. They don't really. But you want to minimize how many that have to actually grade to get a reasonable quality result. And we actually ran those algorithms on the data we collected. But other than that, I haven't actually looked at it to customize the learning experience.
Again, I'm here because I want to say thank you for your course. I'm curious, actually, on the course itself and the structure, I think it's also forward-looking into other people's new courses on online and MOOC or combination. I find the cut ratio was great, but a lot of that, actually, however, I don't care for like 40% of it. I thought the XML, XML was great. I didn't care for, actually, again, I don't want to mention the 40% I didn't care for.
That's why I divided it into 14 mini courses. So now you only have to take the ones you like. In retrospect, that's so obviously the right thing to do. I mean, I taught the course synchronously with the Stanford students, and that was very exciting for the online students. They felt like they were taking this whole Stanford course, which they basically were. And I did that a couple more times. But the way to put it to rest is clearly to break it into these pieces and offer the pieces independently. And luckily for the material in my course, there aren't very many dependencies. So there's just a few places. Wow. There's just a few places where there's really an order that things have to be done in, but people can jump into a lot of them. So I think all courses should be done that way. There's no reason except credentialing, I guess, there's no reason for these to be the size of a university course. Nothing.
I do want to say that the functional dependency was great. I think a lot of...
You like the functional dependencies?
I think actually a lot of people don't do the I mean, they really don't do it. And
well, anybody who wants, I'm afraid I think that same mini course has the multi-value dependencies, which are like the most obscure thing in databases. But anyway, you could turn off the video at that point. But yeah.
So which one, last part of it is, which course have you taken that you liked out there?
Have taken?
Yeah.
I haven't taken a course forever. Boy. No, I have not taken a MOOC myself. Right. I probably should.
Well, which one would you like to?
Oh, if I were going to take a course now, I'd have to take machine learning. I mean, obviously, I've learned machine learning along the way, but I've never done the whole shebang, and no question that would be the thing that I should learn. No question. We all should. Right. No doubt about it. Yeah. All right.